Hello and welcome to your Unit 4/5 video for midterm review. So we're going to go through a crash course of all the things to know for those units. Starting with Unit 4, this is our Systems and Parabolas unit, and the first topic is three variable systems. The big idea here, guys, is that you always want to eliminate the same variable twice. So I'm looking at three different equations. I'm seeing And as I'm analyzing these three equations, I'm looking at my options for x, y, and z. And personally, I think z is going to be the best one to eliminate twice, meaning I can make the coefficients the same but with opposite signs so that when I add the equations together, the z's will drop out. So, eliminate z twice. Okay, so very important to be nice and organized here. So I have my step 1. I am going to work with equations 1 and 3 to start. So let's write them out. Now, the easiest way to eliminate z in this case is by multiplying one of the equations by -1 so that I can create an opposite here. So, what I'm going to do is take the second equation here, multiply it through by -1, and I'll still have the original equation for equation 1, but now I'm going to have the exact opposites for everything for the second, or well, technically the third equation here. Make sure you multiply the 8. Okay, so then, actually don't need those parentheses. I'm just going to add these together, draw the line. 2 z's drop out, and we're left with -2x plus y equals -4. All right, now I got to do z another way. So I think I'm going to work with equations 1 and 2. So again, I'm going to write them out. Now, in order to get them the same but opposite signs, I'm going to have to create a 10z and a -10z. So I think what I'm going to do is multiply the first equation by 5, because that'll create a positive 10z. And then the second equation by -2, so that I create a -10z. Okay, so let's do that. So that's the first line of work. Now here's what's kind of awesome. Not only are my z's going to drop out, but I got lucky and my x's dropped out as well. That does not always happen, but we love when it does. Little double amount of elimination there. Alright, so then when I add these together, I end up with -14y equals 28. So y must equal -2. Awesome. Once you guys have your first variable, you can take that first variable and plug it in to an equation that you have. So it's step 3. I'm going to go back to -2x plus y equals -4, and I'm going to do a little substitution for -2. So 2 over would be -2, so I'm getting x to be +1. Alright, we're almost done. Now that I have two variables, I just go back to one of the original equations. It really doesn't matter which one. I think I'm going to use the first one. So I have 2x minus 4y plus 2z equals 4. And I'm just plugging in what I know. And now from here, you're just solving for z. and after just some algebraic work, I'm getting z equals -3. So my final answer in alphabetical order, I'll write it up here in the upper right, is 1, -2, -3. And that's how you solve a 3-variable system. All right, moving on to the next page, we are going to solve a system, which is actually a line and a circle, both algebraically and graphically. Let's start with algebraically. I'm going to zoom in here. So the idea is you have it already isolated for one variable x. If not, you'd have to do that to start. And what I'm noticing is in the second equation, there's an x right there. So what I'm going to do is take 2y plus 2 and substitute it in for x. So this is what you have. Okay, now I'm going to clean that up a little bit, which creates a 2y minus 1. And here's the rest of your equation that did not have an x to start. All right, so now that you have everything in terms of one variable y, let's do some algebra. Make sure you FOIL here and here. So if you need to, write it out twice to FOIL it. Otherwise, I'm just going to go ahead and FOIL. All right, now from there, I'm going to combine my like terms. I see I have some y squareds, I have some y's, which actually it looks like those drop out, which is pretty awesome for me. And then some constants. So I'm ending up with 5y squared plus 5 equals 25, which is the same thing as 5y squared equals 20. Or y squared equals 4. Don't forget the plus or minus, and y is plus or minus 2. All right, so now that I've gotten my y values, I like to make a little table for myself. So I have y equals 2 and y equals -2. Now going back to the first equation here, x equals 2y plus 2, I'm going to write it down. We're going to take 2 and substitute it in for y, which is 4 plus 2, which is 6. So in alpha order, 6, 2 is my first solution. Now I'm going to use the same thing for y equals -2. So alpha order, -2, -2. And those are my two solutions to the system, which system implies an xy coordinate, which is exactly what I just came up with. Two solutions to the system. Now let's solve this graphically. Okay, so zooming out a little bit here. First of all, this is a line, and I know that because the x is at degree 1 here. Now, anytime we graph a line, we would want it in y equals mx plus b form. So let's rearrange that. Okay, so in y equals mx plus b form, that is my line. Let's go ahead and graph it. So I have a y-intercept at -1 and a slope of 1/2. So up 1 over 2, up 1 over 2. Oops, I went over 3 by accident. Hold on a second. Zoop. Up 1 over 2, up 1 over 2. And some in the other direction as well. And boom, with a little bit of magic, there's my line. So I'm going to go ahead and label it. Y equals 1/2 x minus 1. Okay, cool. Now I got to do my circle. So coming over here, back to this equation. Keep in mind this is a circle with a center at 3, -2. You always just change the signs from what you're seeing. And then your radius is the square root of 25, or 5. So coming on over, let's do some graphing. So again, I said it was 3, negative 2. So that's right here. And then we're going to go 5 in every direction. And boom. So doing the best you can, draw your circle, make it look as round as possible, not rhombus-like, and you should verify those solutions that we just came up with algebraically. Right here is our solution at negative 2, negative 2, so I'll make sure I state it. And right here is our solution 6, 2. Which again verifies algebraically what I did. And that's how you solve a system both algebraically and graphically. As I mentioned before, make sure you label at least one of the graphs, otherwise you do lose a graphing point. Something else we discussed in this unit was parabolas, and particularly we completed the square to put parabolas into vertex form and talked about the transformations that took place. Now, whenever you complete the square, this leading coefficient has to be 1. So I'm just going to put a little note here. CTS means A must equal 1. And as it is right now, it's a 2. So here's how we deal with this. F of x, we're just going to keep chilling over here. And I'm going to move this constant over. So I have f of x plus 40 plus blank equals, and then I'm going to factor out the 2 from these first 2 terms. Now, if you have Miss Costanzo with completing the square, she likes to literally draw a square, so I can do that if you prefer. Now we are all set up to complete the square. What I'm going to do is look right here. This is my B term, because it goes A, B, C. I'm going to take half of that, square it, and that's what I add on the one side of the equation. Now here's the thing though. Remember that 2 we factored out? You're not really adding 9, you're adding 9 times 2. So when I have to balance the other side of the equation, I'm going to put an 18. Alright, so let's simplify this. On the left-hand side, I have f of x plus 58 equals 2, and this is the same thing as x minus 3 squared. Now, you can figure that out using either AM factoring, or I always like to write this because this will always match. That's a nice little factoring hack. Okay, so let's rearrange it. And I think I'm going to use this space over here. I now have f of x equals 2 parentheses x minus 3 squared minus 58, because all I had to do was subtract that 58 over. Now, as far as transformations go, I see 3. Maybe I can like color code it a little bit. This minus 3 right here means we are shifting right 3 units. This 2 is a vertical stretch of 2. And then lastly, this minus 58 means down 58 units. Now, there's some extra info you might be asked about parabolas. One being, where's the vertex? Well, if your parabola normally starts like this, a happy parabola at 0, 0 for your vertex. This is just your base function, y equals x squared. If I went right 3 and down 58, that means your new vertex would be at 3, negative 58. Now, something else to note that you would have just reviewed with Unit 2b, because this is an even degree polynomial, it's up, up, and the leading coefficient is positive, which further means it's up, up. Otherwise, it could have been down, down if there was a negative in front, but there's not. So that means if this is a happy parabola, technically this vertex right here is a minimum. So just some extra information that the problem didn't ask you for, but were also things that we did discuss in this unit. All right, the last thing in Unit 4 that we need to talk about is reasoning systems of inequalities, meaning you guys are going to look at two functions. It looks like this was forgotten to be labeled. Let's call this f of x, and the parabola is g of x. And I want to answer the following questions. So the first one is, for what values of x does f of x equal g of x? Here you're just looking at the intersection points. So here and here. So if I label this, here's my black pen, this is the coordinate -4, 6, and this right here is the coordinate 0, -2. Now this is saying the y's are equal. So for what x values are they the same? So you would say x equals -4 and x equals 0. Again, not the coordinate, this is x's only. Where is f of x greater than g of x? Or where is f of x above g of x? Now, that's kind of an odd question to think about. Another way you guys could think about it, if it helps you, is rearrange it. You could write the inequality like this, keeping little alligator mouth opening the same way. Notice how it's opening towards f of x. This is now saying, where is g of x less than or below f of x? So if you look at your graph, f of x again is the parabola. He's below the line here and here. So the first interval on the left would be from -infinity to -4. But notice how we're looking for where it's below, but not including where they're equal. So we're going to use a soft bracket, which is what this note is in referencing up above. Now, since there's two intervals, we're going to put a union symbol. We pick up again at 0. Again, same thing with a soft bracket. Because there's no equal here, we're going to just use a soft bracket, parentheses, and then forever to the right would be positive infinity. Where is f of x less than or equal to g of x? That is also, again, if it's a hard way to think about it, where is f of x less than g of x? You could think about it as g of x is greater than or equal to f of x. So again, notice how I kept the alligator mouth opening the same way. This is saying, where is your g function above your f function? Again, g is the parabola, so that would have to be this little piece, is above the line. So that interval would be from -4 to 0. But notice how there's an equal sign here. That means we're going to use hard brackets because we want to include those values for which g of x equals f of x. Lastly, where is f of x greater than 0? That's asking, where is the function positive, aka where is it above the x-axis? So looking at my graph, again, f of x is the line. Greater than 0 means positive, so above the x-axis would be here, so where I just highlighted. Now, from left to right, using x values only, we're coming from -infinity, and it looks like it hits the x-axis at -1. And again, we're not going to include -1 because it's just where it's greater. I don't care if it's equal to 0, soft bracket. And those are the intervals when reasoning with our systems of inequalities. In Unit 5, we talked about complex numbers. Okay, which technically every number is a complex number. It's of the form a plus bi, where a is your real component, bi, that's your imaginary. Now, a and b are real numbers, but with the I makes it imaginary. We learned that the square root of -1 is I, and that's where your imaginary unit comes from. Okay, so recall that every number is a complex number. Then it branches off into real versus imaginary. And then real branches off further into rational versus irrational. When you are adding complex numbers, you do real part with real part, imaginary part with imaginary part. It's just like when you're adding like terms. So 10 and 5 is 15. 3 and negative 8i is negative 5i. Done. Okay, and notice how I stated it in a plus bi form. That's the proper way to state your complex numbers. Whenever you're simplifying radicals with a negative underneath, you take out the I first. Square root of 121 is 11. So this is negative 55i. Powers of I. These are the ones we discussed to help us simplify. Okay. Anything to the 0 power is 1. Anything in the first power is itself. Oopsies. I squared is negative 1. That's a biggie. And I cubed is negative I. Okay, so if I'm reducing I to the 24th, I always think to myself, this works in a cycle of 4, right? So 24 divided by 4 is 6, right? See how your remainder is 0? That's going to become my new exponent. Anything to the 0 power is 1. So I to the 24th is equivalent to 1. And that's how you reduce this without a calculator. Sometimes I think I'm faster without a calculator than if I were to plug I to the 24th in, which technically you can on the Regents exam. For I to the 33, I again think to myself, 33 is not divisible by 4, but 32 is. The difference between 33 and 32 is 1. So this technically is going to I. If you want to do the division like I just did in the previous problem, 4 times 8 is 32. Subtract 1. So see how the 1 then becomes the exponent. Okay. For things like 6, if you distribute, if you're multiplying numbers with the same base, you add their exponents. I to the 4th will go to I to the 0 because 4 is divisible by 4. 10 is not divisible by 4, but 8 is, which means my remainder is 2. So I've got 1 plus 3 times negative 1, or 1 minus 3, which is negative 2. And I did that all without a calculator because I personally think I'm faster. Technically, you can plug it in your calculator, though. If I show you real quick, like if I wanted I to the 33rd, oh man, this might show up gross, and because I have the old software on here. Let's see, second decimal is an I to the 33. Okay, it shows up as a gross answer. Negative 3e to the negative 13 is technically 0. 0 plus I is just I. And that does match what I got for number 2. Now, most of you guys have newer software on your calculator, so I to the 33 on like a TI-84C or CE would just spit out I for you, but I have the older software on my computer's, what's this called? I can't even think of it right now. This online calculator that I'm using. This is older software, so that's why it's giving me a weird looking answer like that. Multiplying, same idea. Here you just have to go ahead and FOIL. I won't talk more about that. These guys, if you do FOIL, you'll notice that your inner and outer terms will drop out, because that's 15i and negative 15i. And that's because these are conjugates. Okay, so you really only have to calculate your first and last. Remember that I squared is negative 1. So this goes to 34. Okay, questions like x squared, blah, 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 this one right down here, have come up on the Regents a lot. What you need to do is take this monomial and distribute it through. I get 3x cubed I to the 15th just by adding my exponents. Cubed I to the 8th, again by adding my exponents. And then I reduce. Difference from 12 and 15 is 3. 8 is divisible by 4. So this goes to negative 3 x cubed I. because I cubed is negative I minus x cubed, and technically the correct a plus or minus bi form is this, because this is your real component and this is your imaginary. Now, just like how we can't have radicals in the denominators of fractions, we also can't have i's. So when I rationalize this, I'm going to multiply it by the conjugate of the denominator. Now, since these are conjugates, I only have to calculate my first and last. In the numerator, I'm going to distribute. Now, in the bottom, keep in mind that I squared is negative 1. And do your order of operations. This would go to negative 3. 4 minus a negative 3 would go to 4 plus 3, which is 7. So your final answer is negative 18 minus 9i radical 3 all over 7. So just be careful of order of operations there. All right, the discriminant. It comes from the quadratic formula. So this stuff under here, that's your discriminant. Okay, and what it tells you is the nature of the roots. Make a little flow diagram here. If you get 0 under this radical, that's like saying whatever these numbers are, plus or minus 0. It's not going to make a difference at the end of the day. That's like 2 plus 0 is 2. 2 minus 0 is 2. Okay, and if you divide by the same number, you're just going to get the same answer twice. So when that happens, you're going to get 2 real equal roots. Because you can take the square root of 0. It's 0. Okay, your other option is if you get a positive answer, and technically there's 2 things that can happen. The first thing is you get a perfect square. So let's say like 25. If you get 25 under this radical, you can take the square root of 25, which is 5, and then it's like saying plus 5 minus 5. You're going to get 2 unequal answers because you're adding or subtracting 5, and because you could have taken the square root of 25, they're going to be rational. So you get 2 real, oh yeah, I should have added rational over here. These are rational roots. 2 real, unequal, rational roots. Okay, if you don't have a perfect square, let's say like 27, you can't take the square root of 27 and get an integer value. You're going to get an irrational answer. So therefore, you're going to get 2 unequal irrational roots. The last scenario, which is one of the easiest, is if you get a negative under the radical, like let's say you get negative 36 under the radical, we know that's going to be 6i. So you're going to get an imaginary answer. And technically 2 of them, because you're doing plus the imaginary, take away the imaginary. So you're going to get 2 unequal imaginary roots. All right. So practicing this, if I look at the first guy here and do b squared minus 4ac, 4 minus 4 is 0. So this tells me I'm going to get 2 equal rational roots. Okay, so it allows me to quickly find out what's called the nature of the roots, which is everything I just described up here. Real versus not real, rational versus irrational. Now just to show you why this works, if you were to actually factor this to solve, you'll see algebraically you are getting the same root twice. Negative 1 is rational, so that's why that works. Okay, the next guy, I technically have a 0x in there, so b squared minus 4ac would be negative 16. So this tells me I'm getting 2 unequal imaginary roots. Okay, and then if you didn't believe me, if you actually subtracted the 4 and took the square root, you get 2 solutions, plus or minus 2i. Those are your 2 unequal imaginary roots.
Something else I want to note, this is technically 0 plus 2i and 0 minus 2i. Those are conjugate pairs. So it is important to know that imaginary roots always come in conjugate pairs. And that will be important down below. Let's say I want to build a quadratic equation that would give me imaginary roots. Okay, those are harder to think about. You can't come up with factors and then build going backwards like it's easier with rational values. So in order to do this, we learned that you can build a quadratic by doing x squared minus the sum times x plus the product. That's the sum and product of the roots. Okay, so the sum of these roots would be 5 plus 5, which is 10. Negative I plus I would go to 0. Now the product, I'll actually calculate. I got 25 minus I squared. Remember, I squared is negative 1, so this goes to 26. So my quadratic equation would be 0 equals x squared minus the sum times x plus the product. Okay, let's say I have a polynomial with a bunch of different roots. See how 1 plus 2i is listed? You need to know that 1 minus 2i is also a root. We've just deliberately left it off to test your knowledge that they always come in conjugate pairs. You're never going to have an odd number of imaginary roots because they come in pairs. Okay, so if I figure out the sum of these, 1 plus 1 is 2. The i's would drop out. Okay, so I'm getting 2 and 5, so x squared minus 2x plus 5 would be a quadratic that would give me these roots if I were to solve. Okay, the factor that gives me a root of 0 is x. Okay, and I'm going to put a little star next to that. A lot of students forget that. And lastly, there's a couple ways to think about this. You could either write this as x minus radical 5 times x plus radical 5. And then actually, distribute to get this quadratic. Okay? Or do the sum and product of the roots again. The sum of these roots is 0. The product is negative 5. X squared minus the sum times x plus the product. And you get the same answer. So technically, the polynomial that gives you all of these roots would be the product of these roots. X times x squared minus 5 times x squared minus 2x plus 5. Okay, and then just some vocab for you guys. It says 2 quadratic and 1 linear factor. Yeah, that should say 1. That's your linear, because it's a degree 1 polynomial. These are your quadratic factors, because they have degree 2. All right, we're in the home stretch here. Last couple things to talk about. I'm going to algebraically solve for all my zeros here. This is x squared. I need factors of 144 that sum to 7. Let's say I don't know these. I can go to my y equals. And do 144 divided by x. So ones that sum to 7. Is that what it was? Or negative 7. Nine and 16. Okay, but I'm going to make this be positive. Okay, because positive 9 and negative 16 sum to negative 7. Okay, now if I set each of these equal to 0 and solve, I get 2 imaginary solutions out of x squared plus 9. I get plus or minus 3i. Over here, I get 2 real solutions, plus or minus 4. So how many solutions are complex? That's all of them. 4. And note how the 4 matches the degree of the function. That will always happen. How many are real? Those are just your x-intercepts. Okay, so 2 are real. So state the number of x-intercepts. That's your real solutions only. How many are imaginary? That's these guys over here. 2 plus 2 will give you 4. All right, one last problem. I give you a function and a graph of it, so this is k of x. I want to know what the real roots are. That's where it crosses the x-axis. So -1 and 5. Whoa. Now, if it asked me for the real factors, keep in mind that would be x plus 1 and x minus 5. So just keep straight the vocab, okay? We're going to use polynomial division to help us rewrite this function in terms of 2 linear and 1 quadratic factor. Okay. I'm going to use these to essentially break down this polynomial using synthetic division. So let's divide out by the root of -1 first, just because I think it's easier. And you should get 0. If you don't, you made a mistake. Because this is a factor, or this is a root of this polynomial. So when you divide out by it, you should get a remainder of 0. We would never lie to you. Alright, so then this continues. So now I'm going to divide out by a new root of 5. And again, you should get 0. Now keep in mind, you had a 4th degree divided by a 1st degree and then another 1st degree, so 4 minus 1 again is 2, so technically this is x squared plus 4. That's your quadratic factor. So if I want to rewrite k of x, it's going to be x squared plus 4 times the factors that gave me these roots, which I actually already previously calculated. I just erased them. The factor that gives me a root of -1 is x plus 1. The factor that gives me a root of 5 is x minus 5. And then you're done.